In this video, we will practice modeling data using linear, quadratic, or cubic functions. This is AP Precalculus topic 1.13 and 1.14. If you appreciate this content, please give it a like. We are starting with number 10. What happened in numbers 1 through 9? Don't worry about it. The table below shows the amount of money in billions of dollars spent on public education from 2010 to 2014. Part A, find a regression equation. They will always specify this on the AP exam, so I'm going to add in let t equals 10 represent the year 2010. Now we can type this data into the graphing calculator. Hit the Stat button and hit Enter. Let's enter the year in L1 and let's enter the annual spending in L2. We were not told what type of regression model to use, so let's make a scatter plot to see if the data appears roughly linear, quadratic, or what. Hit the Y equals button. We need to turn on plot 1, so let's just get on up here and hit Enter. If you now hit zoom 9, which is zoom stat, then it should give you a good graph. So there's my scatter plot. I'm going to say that this appears roughly linear. So let's hit Stat, switch over to the Calc menu, and let's do a linear regression model. I'm going to do the AX plus B. Sometimes they will specify whether they want you to do AX plus B or A plus BX. You're going to get the same answer to the next part either way. So I'm picking option 4. Always store the regression equation into y1. So let's go ahead and say alpha trace and just hit Enter for y1. That way, if we need the regression equation to answer a different question, it'll automatically be there. Hit Enter a couple of times and kabam! Here is our linear regression model. Let's copy it down. Part B, use the equation to estimate the projected spending for 2018. So we need to evaluate y at 18. We can do this in the graphing calculator. Go to a blank screen, and we can pull up y by doing alpha trace enter, because we stored the regression model as y1. To evaluate y1 at 18, just put an 18 next to it in parentheses like this and hit Enter. Let's see, that's a little bit off camera. 841.904. Don't forget your units. $841.904 billion. Number 11. The table below gives the number of licensed drivers in the U.S. and the population in the U.S. from 2010 to 2013. Find regression equations for Part A, year versus population. Let's type this data into the calculator, again letting t equals 10 represent the year 2010. By the way, to clear out the data in a list, go up to the title and hit Clear and Enter. Now just enter this population data in L2. Let's take a quick look at the scatter plot. Plot 1 is still on from before, so we can just go ahead and hit zoom 9. This data looks very linear, so let's use a linear regression model. Hit Stat, switch over to Calc, and let's choose option 4 again. Always tell your calculator to store the regression equation as y1. So hit alpha, trace, Enter, and then hit Enter a couple more times. And here's your regression model. Before we move on to Part B, I'm noticing that Part C is to use the equations to predict the amounts for 2018. We should probably do this for the year versus population while the regression model is still in the calculator. So we can do y at 18 to predict the amount to predict the population in 2018. Of course, you could manually type in the whole regression model with an 18 plugged in, and that wouldn't be too bad for this particular equation. It didn't have a bunch of decimals in it or anything. Or you can hit alpha, trace, enter, and just put the 18 in parentheses like this. So, 327,483. The population data was in thousands, so this number represents 327,483,000 people, or it would be more natural to think of this as 327,483,000 people. Part B, let's now find a regression model for year versus licensed drivers. So we just need to enter this data in L2. We will again hit Stat, switch to Calc, Option 4. We will again store the regression model as Y1. So you know what, I guess we could have stored it as Y2 and then that wouldn't have erased it. But anyway, alpha, trace, Y1. Enter, enter. There it is. To distinguish these two models, I'm going to call the first one P for population, and I'm calling the new one D for drivers. So for part C, we need to evaluate D at 18 to estimate the number of drivers in 2018. Back to the calculator. So we can hit alpha, trace, enter, and then put in the 18 with parentheses. And there it is. Don't forget your units, which is in thousands of drivers. This is the same as 215,440,000. Number 12. The table lists the cost of 2% milk. Use a scatter plot to answer the following questions. Let's continue to let t equals 10 represent the year 2010. Notice that we will have to enter a -2 for 1998. Part A. Describe the trend of the data. Is there a clear correlation? Here's the data typed in. Let's hit y equals and make sure that plot 1 is on. Let's clear out the old equation and hit zoom 9. So this data appears roughly linear. The cost increases as the year increases at a roughly constant rate. Part B, find the regression equation. Linear regression model. So stat, switch to calc. Let's choose option 4. And before we hit enter, let's go down to store regression equation into alpha trace y1. Hit enter a couple more times. And there it is. The College Board only requires 3 decimal places, but last year many students lost points because they rounded wrong. So I'm going to suggest that you record your answer with 4 decimal places without rounding, like this. Part C, based on your linear model, how much would you expect to pay for a gallon of 2% milk in 2015? In other words, we need to evaluate y at 15. To the calculator. Never use the rounded numbers. Instead, let's do alpha trace enter to use the equation stored in y1, which includes all the decimals. So we just need to do y1 at 15. And there it is. Don't forget your units, which are dollars. And again, I recommend recording your answer using 4 decimal places unrounded. But the College Board will accept 3 decimal places for both answers. For the rest of these problems, we will write an equation to model the scenario and then solve. Number 13. The diameter of the largest particle that can be moved by a stream varies directly as the square of the velocity of the stream. A stream in the Great Smoky Mountains has a velocity of 2 miles per hour and can move coarse particles about 0.2 inches in diameter. What velocity is required to carry particles 0.5 inches in diameter? Quick side lesson. Y varies directly as x means that y equals k times x for some constant k. Y varies inversely as x means y equals k divided by x for some constant k. This phrasing shows up in many modeling problems, so make sure you understand that this phrase means this equation and this phrase means this equation. So when they say the diameter varies directly with the square of the velocity, that means that d is equal to k times the velocity squared for some constant k. A stream with a velocity of 2 miles per hour can move particles 0.2 inches in diameter. We can use this input-output pair to find the value of k. So 0.2 is equal to k times 2 squared. 0.2 is equal to 4k. Dividing both sides by 4, we get k is equal to 0.2 divided by 4. Assuming this problem is calculator active, we could just do this. K is 0.05. Here's what you would do if this showed up on a problem that was not calculator active. Understand that 0.2 is the same thing as 2/10. So 0.2 divided by 4 is really 2/10 divided by 4. And 2/10 reduces to 1/5. So we have 1/5 divided by 4. When you divide a fraction by an extra number, you just multiply that number into the denominator. So 1/5 divided by 4 is the same thing as 1/5 with a 4 in the denominator. So this is 1/20. So k is equal to 1/20, which is equivalent to 0.05. If this was a non-calculator active problem, we would simply use this value for the rest of our calculations instead of the decimal. Now that we have found the value of k, our model becomes d equals 0.05 times v squared. We need to find the velocity that is required to move a 0.05 inch particle. At d equals 0.5, we have 0.5 equals 0.05 v squared. Dividing both sides by 0.05, we get 10 is equal to v squared. Taking the square root of both sides gives us v is equal to the square root of 10. That's 3.1622. Don't forget the units, 3.1622 miles per hour. Again, I recommend using 4 decimal places, unrounded, just to be safe. 14. Ryan has 3,000 feet of fencing to enclose a rectangular field for his horses. One side of the field lies along the river, so only 3 sides require fence material. See the image below. Part A. Express the area of the rectangle as a function of the width x of the rectangle. We know that the formula for the area of a rectangle is base times height. So that would give us area is equal to x times y. But we need an expression that is only in terms of x. So we need to replace this y with something. Think of the area equation as the primary equation because that's what we are being asked to find. However, to rewrite this in terms of x, we need to start with a secondary equation that will come from the fact that we have a total of 3,000 feet of fencing. That means that x plus y has to add up to 3,000. In other words, x plus 2y must equal 3,000. Our goal is to get y by itself, so we can have an expression that we can substitute for y. Let's subtract x from both sides, giving us 2y is equal to 3000 minus x. Finally, let's divide both sides by 2. Y equals 1500 minus 1/2 x. Let's substitute this expression for y in the area equation. Area equals x times the quantity 1500 minus 1/2 x. This could also have been written as area equals 1500x minus 1/2 x squared. Part B, what is the domain of the area model? Well, x represents the length of this side of the fence, and it cannot be 0, so x has to be definitely greater than 0. But is there any upper limit to what x can be? We only have 3,000 feet of fence, so x has to be less than 3,000. If we had a really ineffective fence that had teeny tiny y's, like maybe this was 0.5 and this was 0.5 over here, and that would leave 2,999 feet for x. But the x has to be something less than 3,000. Part C, using a graphing utility, find the value of x that produces the largest area. Let's put this model as y1 in the graphing calculator. When you type it in, it's going to look like this. We need to turn off the plot from our previous problems, or this will cause trouble. So go up to this and hit enter to turn that plot off again. Now it's time to adjust the window on the calculator before we look at the graph. Remember that the domain of x is from 0 to 3,000. So hit that window button, and let's let x min be 0, and let's let x max be 3,000. But what about y min and y max? Obviously, the y min will also be 0. In this case, the y that we're talking about is not this y. It's the value of the function itself. So 0 means 0 area. Let's get a sense for how big the maximum area might be. Let's imagine that this was a square. 1,000 times 1,000 is 1,000,000. So the area could be easily that big. So I'm going to make y max be over 1,000,000. I'm going with 1,500,000. Let's hit graph and see what we've got. Okay, so the max is going to be right there. So let's hit second trace and choose option 4 for maximum. When they ask for the left bound, just move the pointer somewhere that's definitely to the left of the max and hit enter. Now it's asking for the right bound. Slide over somewhere to the right of max and hit enter. Then it says guess. Just slide back somewhere near the max and hit enter. So there it is. The maximum value will occur at x equals 1,499.9998. So that's it for number 14. Number 15. Water is poured into a container in the shape of a right circular cone with radius 4 inches and height 16 inches. Express the volume of the water in the cone as a function of the height h of the water. They gave us the primary equation, the volume formula, but this is written in terms of r and h. We want it only in terms of the height h. That means we need to write a secondary equation that we can solve for r to substitute right here. This comes up in calculus a lot. We are going to use similar triangles from geometry class. For example, the red triangle and the blue triangle are similar triangles, so we can write an equation involving r by thinking small over big equals small over big. R over 4 should equal h over 16, small over big. This is our secondary equation. Let's get r by itself so we can get an expression that can be used to substitute for r. Multiplying by 4 on both sides gives us r is equal to 4h over 16. But 4 goes into 16 4 times, so this is really r is equal to 1/4 h. We can substitute this expression for r right here. This is one version of the answer. We were asked to express volume as a function of height, and we've done that. But let's continue and simplify a little bit. If you square 1/4 and h, you're going to get 1/16 h squared. So we have volume is equal to 1/3 pi times 1/16 h squared times h. This will simplify it further. 3 times 16 is 48. So we have, I started to say 1 over 48 pi, but let's go ahead and put this pi in the numerator. So we can just say pi over 48, and then h squared times h is h to the 3rd power. So this is the better answer. And if this were a multiple choice question, you would not find this equation as an option, you would find this. Number 16 is a common problem that is likely to show up somewhere on the AP exam. You will also see it again next year in AP Calculus. A square of side x inches is cut out of each corner of a 9-inch by 12-inch piece of cardboard, and the sides are folded up to form an open-top box. And then we have these questions. First, let me try to help you visualize what the problem is talking about. We are starting from a rectangular piece of cardboard, 9 inches by 12 inches. We are going to cut out the corners in the shape of squares that are length x on a side. This blue outline is what's left of the cardboard after we cut out the corners. If we fold up the 4 flaps, we get an open top box that has this light blue rectangle as its base. Part A, write the volume V as a function of its side x. We know that the volume of a box is length times width times height, so we need an expression for each one of these dimensions. The width of this box is the width of this light blue rectangle, which is 9 minus the 2 x's that were cut out. So this width is 9 minus 2x. Similarly, this length of the box is this length of the light blue rectangle, which is 12, again minus the 2 x's that were cut out. The height of the box is the size of the cut, so the height of the box is x. The volume will be the width times the length times the height. So the volume will be given by this expression. Part B, state the domain of the function. Well, x represents the size of the cut. So if you had no cut at all, that would be size 0. So x has to be something bigger than 0. So I'm going to write 0 is less than x. But is there some maximum value of this cut? The cut size x is going to be limited by the original dimensions of the cardboard, the 9 and the 12. However, the 9 is the smaller dimension, so that's the one that is really going to limit the size of this x. Does that mean that x can be anything between 0 and 9? Well, not so fast. Remember that we have to cut 2 equally sized squares from this width. The sum of the 2 cuts has to be less than 9, so each cut must be less than 4.5. So the domain is x is between 0 and 4.5. Part C, graph function v to find the maximum volume of the box. Let's enter this equation as y1 on the graphing calculator. It's going to look like this. Before we graph, we need to adjust the window. Remember, the domain of x is between 0 and 4.5. So let's start by hitting the window button and setting x min to 0, and x max will be 4.5. What about the y min and y max? The y value represents the volume. So y min will be 0 for 0 volume. The y max is the maximum volume, which we don't know and we're trying to find. So let's just find an example volume. Imagine that x is 1. Then the volume would just become 9 minus 2 times 12 minus 2. 7 times 10, that's 70. So that's one example volume of 70. So let's let y max be something that's bigger than 70, but not a crazy amount bigger. Let's go with 100. Let's hit graph and see what we've got. The maximum volume is going to be right here. I'm looking back at the question to see if they asked us to find the x value or the y value. This time they ask us to find the maximum volume. That's going to be the y value. Let's do second trace, option 4 for maximum. For left bound, move your pointer to the left of max and hit enter. For right bound, move the pointer to the right of max and hit enter. For the guess, move the pointer near the max and hit enter. The maximum volume is the y value, which is 81.8721. Don't forget the units, which would be cubic inches. If they had asked what size cut gives the maximum volume, well, now they're asking for the x value. This was 1.6972. And the units on that would simply be inches. Number 17. The table below gives the stopping distance for an automobile under certain road conditions. Part A. Find a linear model for the data. Let's enter this data as L1 and L2 on the graphing calculator. So stat, enter, and type it in like this. They want a linear regression model, so let's hit stat, switch over to the calc menu, and choose option 4. Before calculating, let's go down and tell it to store the regression model as y1. So alpha, trace, enter. Now hit enter a couple more times. And there's your model. I'm using L for linear instead of Y because I see that next we're going to be doing the same thing with a quadratic model, which I will call Q. Follow my example and use 4 decimal places without rounding. Just trust me, this will save you a point or two on the AP exam due to avoiding rounding errors. Part B says find a quadratic model, so let's go back to the calculator. Hit stat, calc, but this time choose option 5 for quadratic. Because we already have an equation stored in y1, and I don't want to delete over it in case we need it, we can store this equation as y2. Just remember where you put it. Hit alpha trace, but let's choose y2 this time. Hit enter a couple more times. Kabam! There is your regression model. So there's your quadratic model, but now for part C we need to compare the models and see which one's better. Let's take a look at the scatter plots. We probably need to turn the scatter plot on, so hit y equals and go up to plot 1 and hit enter. Zoom 9 will usually give you a pretty good scatter plot, so let's hit zoom 9. We can see that the quadratic model shown here in red is a better fit, But when you are asked to explain why one model is better than another, you are not allowed to say, well, I looked at the scatter plot on my calculator and the quadratic was a better fit. So what do we say instead? We want to say something about how the rate of change is changing. If the data had appeared linear, of course we would have chosen the linear model. For the explanation, we would say that the rate of change is roughly constant. When the data appears concave up like this, we're going to pick the quadratic model as the better fit, but for the explanation, we say the rate of change is increasing. The quadratic model is more appropriate because the rate of change of the data is increasing. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.